Hello and welcome to today's video. Today we will be solving the heat equation via a method called separation of variables. So, separation of variables. Now, the solution to this equation will be quite long, so I'll be splitting the video into several parts. This is part 1. So, the heat equation is as follows. Partial dy by dt is equal to kappa squared times partial d squared y by dx squared, where we have x is bounded between 0 and 2, and time is always greater than 0. Always non-negative. In this case, kappa squared is equal to a half, and we have Dirichlet boundary conditions, which is the function evaluated at 0 is equal to 0, and at 2 is equal to 0 for any time. And we've been given initial data. Also, where at time equals 0, we have this function as the solution. So, how do we actually go about solving this kind of equation? Well, we need to use something called separation of variables. And so what that is it's assuming that our function x and t follows a certain form, which is a function solely of x multiplied by a function solely of t. Okay? That's the way we're going to do it. So, inserting our boundary conditions into here, we have now x of 0 is equal to 0. Now this implies that for any t, x of 0 is equal to 0. So for a particular value of t, where t of t is not equal to 0, this follows that x of 0 must be equal to 0. And similarly, x of 2 times t is equal to 0. This must follow that x of 2 is also equal to 0. Okay? So, now inserting our function into our PDE, we have on the left hand side x of x t primed t is equal to 1/2 multiplied by x double prime by t. Okay, now we will do a trick, and this trick is dividing by x of x t of t on both sides. So this will give us t primed of t divided by t of t is equal to 1/2 x double primed of x over x. And the only way that the left hand side is equal to the right hand side is if both sides are equal to a constant. And we're going to call that constant lambda. And this has a special word because it comes up a lot in PDEs, and it's called the separation constant. And this must be the case because this left hand side is solely dependent on t, and the right hand side is solely dependent on x, so there's no way that they can be equal unless there is no x or t in the equations, and hence the equations are constant. So this allows us to form two ODEs from one PDE. First ODE is the left hand side, and the second ODE is the right hand side. Like so. And hence, since you're at this stage, I will assume you know and are capable of solving these differential equations. So we will just go through the solutions. So we will solve number 2, and then we will use that solution to find an answer for number 1, since we have initial conditions for number 2 over here. So solve 2. So this is the second equation, and we don't know what lambda is. All we know is lambda is a number, is a constant. Lambda could be equal to 0, it could be less than 0, where it's equal to some negative mu squared, or it could be greater than 0. And I'll explain why we've used a square in a second. So case 1. This is where lambda is equal to 0. Well, then we have the ODE which follows and of course, let me just remind you, this is the function on the left hand side, and this is on the right hand side, this is the variable. So inserting our initial conditions, we have which follows that b is equal to 0, and the second initial condition is which follows that a is equal to 0. This is from up here. Hence we have a trivial solution. So let's go to case 2. Case 2 is where lambda is greater than 0. So our ODE then becomes which gives us this. Now, how do we solve this kind of ODE? Well, we have to use an auxiliary equation. So we introduce a new variable, s. And hence we find we have the solution is these two roots here. So then the solution to this ODE then becomes the following. Okay, brilliant. Now let us insert our initial conditions. Inserting our initial conditions and doing a little bit of algebra, we find that a must be equal to b, which is also equal to 0. So we also have a trivial case. So there's only one more case to consider, which is that lambda is negative. So then our ODE becomes x double primed minus 2 times minus mu squared times x is equal to 0. Simplifying this, we get x double primed plus mu squared x is equal to 0. 2 mu squared x is equal to 0. Again, using our auxiliary equation, we introduce two new variables, s squared plus 2 mu squared is equal to 0. So it follows that the solutions are s is equal to plus minus root 2 mu I. Hence, the general solution follows that x must be equal to a times cosine root 2 mu x plus b times sine root 2 mu x. In the next video, we will be finishing off this form, finding out a value for mu, then inserting it back into the ODE number 1, then using our initial data to find the general solution for the PDE. See you in the next video.